Welcome to your Chapter 15 lecture. Chapter 15 focuses on surveying the stars. So on a clear, dark night, a few thousand stars are visible to the naked eye. Many more become visible through binoculars, and a powerful telescope reveals so many stars that we could never hope to count them. Like each individual person, each individual star is unique. Like all humans, all stars have much in common. Today we know that stars are born from clouds of interstellar gas, and they shine brilliantly by nuclear fusion for millions to billions of years, and then die sometimes in really dramatic ways. In this chapter, we'll discuss how we study and categorize stars and how we've come to realize that stars, like people, change over their lifetimes. So in the first section, we have to talk about the properties of stars. We only see a brief moment in any star's life, and our collective snapshot of the heavens consists of frozen moments for billions of stars. From this snapshot, we've been able to learn and reconstruct the life cycle of stars. We now know that all stars have a lot in common with the sun. We're going to see and talk about how they formed in great clouds of gas and dust and begin their lives with roughly the same chemical composition as the sun, which is about 3/4 hydrogen and 1/4 helium, with no more than 2% consisting of heavier elements. Nevertheless, stars are not all the same. They differ in size, age, brightness, and temperature. So we're going to focus kind of the next 2 chapters to understanding how and why stars differ. First, what we're going to do is explore how we measure 3 of the most fundamental properties of stars. We're going to learn how we measure stellar luminosities, stellar temperatures, and stellar mass. So we're going to start with how do we measure stellar luminosities? If you go outside on any clear night, you're immediately going to see that stars differ in brightness. Some stars are so bright that we use them to identify constellations. Others are so dim that our naked eyes can't see them at all. However, these differences in brightness do not by themselves tell us how much light the stars are generating, because brightness also depends on temperature. So we're going to define now luminosities and kind of how we measure brightness of a star. Because 2 similar looking stars can be generating very different amounts of light, we need to distinguish clearly between a star's brightness in our sky and the actual amount of light that it emits into space. When we talk about how bright stars look in our sky, we're talking about apparent brightness. So apparent brightness is how bright a star looks in our sky. More specifically, we can define the apparent brightness of any star in our sky as the amount of power, which is the energy per second that reaches us per unit area. So kind of a more formal definition of apparent brightness is the amount of light reaching us per unit area from a luminous object. When we talk about how bright stars are in an absolute sense, regardless of their distance, that's when we talk about luminosity. Luminosity is the total amount of power that a star emits into space, and that's usually measured in watts or in units of solar luminosities, which we write as L sun. So we can understand the difference between apparent brightness and luminosity by thinking about a standard light bulb, for example. The light bulb always puts out the same amount of light, so its luminosity does not vary. However, its apparent brightness depends on our distance from the bulb. When we stand very close to a light bulb, it looks very bright. But if we're far away, it looks very dim. So apparent brightness is how bright the stars are from where we are on Earth, whereas luminosity is the total amount of power that the star emits. The apparent brightness of a star or any other light source obeys an inverse square law with distance. So what that means is the further away you get from the star, the more dim it is. We don't see it as bright. The same total amount of light must pass through each imaginary sphere that surrounds the star. What we see is the amount of light received per unit area decreases with increasing distance, which means that it goes through and applies the inverse square law. So if we increase the distance, they look less bright and they'll look more dim. This inverse square law leads to a very simple and important formula relating apparent brightness, luminosity, and distance of any light source. So we're going to call this the inverse square law for light. And this tells us that the apparent brightness equals the luminosity divided by 4 pi times the distance squared, which basically this part on the bottom here is the area of a sphere, which is why that kind of makes sense. Because the standard units of luminosity are watts, the units of apparent brightness are typically watts per meter squared. In principle, we can always determine a star's apparent brightness by carefully measuring the amount of light per square meter that we receive from the star. We can then use the inverse square law to calculate a star's luminosity if we can first measure its distance, or to calculate a star's distance if we somehow know its luminosity. So we could take this equation and kind of manipulate it and move it around to learn luminosity, distance, or apparent brightness, depending on which one of those variables we know. The next thing we're going to look at is measuring distance through the stellar parallax. And the question we want to answer here are, how far away are these stars? The most direct way to measure a star's distance is with its stellar parallax, which is the small annual shifts in a star's apparent position that's caused by Earth's motion around the sun. Astronomers measure stellar parallax by comparing observations of a nearby star made 6 months apart. The nearby star appears to shift against the background of a more distant star because we're observing it from 2 opposite points of Earth's orbit. We can calculate a star's distance if we know the precise amount of the star's annual shift due to this parallax. This means that we can measure an angle that we call P, that we call the parallax angle. So the parallax is just this apparent shift in the position of a nearby object against a background of objects that are farther away. So we can judge the apparent positions of our closest stars by looking at how their position shifts caused by Earth's motion around the sun. We measure this by comparing snapshots taken at different times and measuring the shift in the angle to that star. So what that looks like is kind of here on this slide. So we said we can calculate a star's distance if we know the precise amount of the star's annual shift due to the parallax. So what we're measuring here is the angle P that we call the star's parallax angle. So this angle would be smaller if the star were farther away, meaning that more distant stars have smaller parallax angles. The real stellar parallax angles are actually very small. Even the closest ones have angles smaller than 1 arcsecond. So you'll see we measure that angle at 2 different points in times that are 6 months apart. So we have those 2 measures of P here. We compare that position of the nearby star against the background of distant stars. So for example, in January, we would see this, and that's the star that we're looking for. And every July, we'd see that, and that is the star that we're looking for. So that position of that star against the background helps us determine that stellar parallax. And that parallax then helps us determine distance. By definition, the distance of an object with a parallax angle of 1 arcsecond is something we call 1 parsecsecond. The word parsec comes from combining the words parallax and arc seconds. If we use units of arc seconds for parallax angle P, a simple formula shows us how we can calculate the distances in parsecs. 1 divided by that parallax angle gives us the distance in parsecs. Astronomers often state distances in parsecs, kiloparsecs, or megaparsecs, but with a little bit of geometry, we can actually show that 1 parsec is equivalent to 3.26 light years. So then we can actually figure out the distance in light years by using this formula here, where the distance in light years is equal to 3.26 times 1 over P, where P is that parallax angle. So I know that probably sounds a little bit confusing. Big picture point, the way that we measure a star's distance is by using that stellar parallax, which the way we do that is by measuring small annual shifts in a star's position relative to more distant stars. That's kind of just a summary of how we use stellar parallax to determine distance, and here's the formula that allows us to do so. Now we're going to look at the luminosity of range stars. We usually state stellar luminosities in comparison to the sun's luminosity. So L sun is the luminosity of the sun. Overall, our studies of luminosities of many stars have taught us 2 really important lessons. First, stars have a wide range of luminosities, and our sun is somewhere in the middle. The dimmest stars have luminosities 1 over 10,000 times that of the sun, which is 10 to the negative 4 L sun, while the brightest stars are about 1 million times as luminous as the sun, which we call 10 to the 6 L suns. Low luminosity stars are more common than high luminosity stars. For example, even though our sun is roughly in the middle of the overall range of stellar luminosities, it is more luminous than most of the stars that exist in our Milky Way galaxy. We can also measure apparent magnitude and absolute magnitude of stars by using what we call the magnitude scale. Lowercase m is the apparent magnitude, while capital M is the absolute magnitude. So we could figure out the apparent magnitude by taking the apparent brightness of star 1 divided by star 2 and using this equation here. Same thing with luminosity. If we have the luminosity of star 1 and star 2, we can then figure out with this equation and look at absolute magnitudes. Now we can answer our next question. How do we measure stellar temperatures? A second fundamental property of a star is its surface temperature. You might wonder why we emphasize surface temperature rather than interior temperature for stars. The answer is that only surface temperature is directly measurable. The interior temperatures of stars are inferred from mathematical models of stellar interiors. When we hear an astronomer speak of the temperature of a star, we can be pretty sure they mean the surface temperatures unless they say otherwise. Measuring a star's surface temperature is somewhat easier than measuring its luminosity because the star's distance doesn't affect the measurement. Instead, we determine the surface temperature of a star from either the star's color or the star's spectrum. So we're going to look at that in the next couple of slides. And we're going to start by looking at color and temperature. Stars come in almost every color of the rainbow. Simply looking at the colors tells us something about the surface temperatures of the stars. For example, a red star is cooler than a yellow star, which is cooler than a blue star. So what we see is the blue stars are the hottest and our red stars are the coolest, which is kind of backwards of what we would think. Some stars come in different colors because they emit thermal radiation. Remember that a thermal radiation spectrum depends only on the surface temperature of the object that emits it. And remember that every object emits thermal radiation with a spectrum that depends on its temperature. So that's why we can use color to infer the temperature of a star. Typically what we see is an object of a fixed size grows more luminous as its temperature rises. So it becomes brighter as it becomes hotter. So we see those two important properties of thermal radiation. One, hotter objects emit more light per unit area at all frequencies. Second, hotter objects emit photons with a higher average energy. So if the temperature is hotter, we see that there's more light, and that light is at higher frequencies. And typically they have a higher energy associated with them. So larger objects can emit more total light even if they are cooler, just because they happen to be larger, because intensity is done per area. So that's important to remember here. So our first thought question of the day, the radiation from a star gives temperature information for which part of the star? A, the core, B, the surface, C, the radiation zone, or D, the convection zone. The answer here, the radiation from a star gives the temperature information for B, the surface of a star. So anytime we're talking about the temperature of a star, we're talking about the temperature of its surface. Continuing to learn about stellar temperatures, our hottest stars are somewhere around 50,000 Kelvin. The coolest stars are about 3,000 Kelvin, and the sun's surface is around 5,800 Kelvin. So we see the sun's not the coolest, but it's not the hottest. It's kind of a medium-ish star. The hottest ones are blue, the coolest are red, and in between we kind of have yellow, orangey colors. Now we're going to look at spectral types and temperatures. A star's spectral lines provide a second way to measure its surface temperature. In fact, because interstellar dust can affect the apparent colors of stars, temperatures determined from spectral lines are considered more accurate than temperatures determined from colors alone. Stars displaying spectral lines of highly ionized elements must be fairly hot because it takes a high temperature to ionize atoms. Stars that have spectral lines of molecules must be relatively cool because molecules break apart into individual atoms unless they're at cool temperatures. The types of spectral lines present in a star's spectrum gives us a direct measure of the star's surface temperature. So we look at the absorption lines in a star's spectrum to tell us its ionization level, which we then can correlate to high or low temperatures. Astronomers also classify stars according to a surface temperature by assigning a spectral type determined from the star's spectral lines that are present in a star spectrum. The hottest stars with the bluest colors are spectral type O, and then getting to cooler temperatures and redder colors, we then have spectral types B, A, F, G, K, and M. So we actually classify stars by using those. So the hotter stars with the bluest colors are O, going to cooler, redder stars. This is the order we see in spectral types. So our next thought question here, just to make sure we have this color and temperature thing down, which kind of star is hottest? A, an M star, B, an F star, C, an A star, or D, a K star? And the answer here, which star is hottest, is C, an A star, because remember the order from hot to cool is O, B, A, F, G, K, and M. So if we were looking at the stars listed here, A is the hottest kind of star. So how do we measure stellar masses then? Well, mass is generally more difficult to measure than surface temperature or luminosity. The most dependable method for weighing a star relies on Newton's version of Kepler's third law. Remember that this law can be applied only when we observe one object orbiting another, and it requires that we measure both the orbital period and the average orbital distance of that object. For stars, these requirements generally mean that we can apply the law to measure masses only in binary star systems. Binary star systems are ones where two stars continually orbit each other. So how do we measure stellar masses? Well, we have to use Newton's version of Kepler's third law, and usually this is good for binary star systems. Which is kind of what we're seeing in this image here. We see two stars kind of orbiting each other. So there's actually different types of binary star systems. Typically they fall into three classes: visual binary, spectroscopic binary, and eclipsing binary. About half of all of our stars are actually in binary systems. This is an example of a visual binary star system. A visual binary is a pair of stars that we can see distinctly as the stars orbit each other. Typically, we need a telescope to see them. So visual binary are ones we can directly observe the orbital motions of these stars. Sometimes we observe a star slowly shifting position in the sky as if it were a member of a visual binary, but its companion might be too dim for us to see. So visual binaries are ones that we can directly observe the motions of these stars orbiting each other. A spectroscopic binary is identified through observations of Doppler shifts in its spectral lines. If one star is orbiting another, it periodically moves toward us and away from us in its orbit, which means its spectral lines will show alternating blue and red shifts. Sometimes we see two sets of lines shifting back and forth, one set from each star of the two stars in the system. Other times we see a set of shifting lines from only one star because its companion might be too dim to be detected. So we determine the orbit of these binary stars by measuring its Doppler shifts. It's blue shifted when it's approaching us, it's red shifted when it's receding from us. And finally, we have eclipsing binary. This is when we have a pair of stars that orbit in the plane of our line of sight. When neither star is eclipsed, we see the combined light of both stars, and that's what we're seeing here on the left. When one star eclipses the other, the apparent brightness of the system drops because some of the light is blocked from our view. So we see all of the light from B, but only some of the light of A here. Again, in this position, we see both A and B. When it's in the other eclipse position, we see light only from A because B is completely hidden. So we see these drops in brightness here. So for eclipsing binary stars, we can measure those periodic eclipses and see that change in apparent brightness. So now we can look at how we measure stellar masses and radii in the binary systems. Even for a binary system, we can apply Newton's version of Kepler's third law to help us calculate mass only if we measure both orbital period and the separation of the two stars. We can directly measure orbital period for all three binary types, but determining the average separation of the stars in a binary system is usually the difficult part. So we kind of can see the distance between the stars, and that's what we want to measure here. So in order to measure mass, we need two out of these three things that we can observe: orbital period, orbital separation, which is simply like the radius, it's the separation between the two stars, or orbital velocity. We can also measure mass directly using gravity. Direct mass measurements are possible only for stars in binary systems. So we use this equation here to help us learn about the period, which can help us figure out these direct mass measurements using gravity. Through careful observations of eclipsing binaries and other binary star systems, astronomers have established the masses of many different kinds of stars. Overall, the range stems from as little as 0.08 times the mass of the Sun, which we call M-Sun, to at least 150 times the mass of the Sun, which is 150 M-Sun. So there really is a wide range of masses of stars. So in this section, we learned how we measure stellar luminosities. If we can measure a star's apparent brightness and distance, we can then compute its luminosity using the inverse square law for light. And the parallax can tell us our distances to the nearest stars. We also learned that we can measure stellar temperatures using a star's color and its spectral type, because both will reflect the temperature of the star's surface. Finally, we learned how to measure stellar masses using Newton's version of Kepler's third law, which tells us that the total mass of a binary system, if we could measure the orbital period and the average orbital separation of the system, meaning how far apart the two stars are. Now in this section, we're going to learn about the patterns among our stars. We have seen that stars come in a wide range of luminosities, surface temperatures, and masses. But now we want to see, are these characteristics randomly distributed, or can we find patterns that might tell us something about the stellar lives of these stars? So in this section, we're going to learn what a Hertzsprung-Russell, or HR diagram is. We're going to learn what the significance of the main sequence phase of stars is. We're going to learn about what giant supergiants and white dwarfs are, and why the properties of some stars vary. So first thing, we need to learn what a Hertzsprung-Russell diagram is. It's often also called an HR diagram, and it's named after the two scientists that created it. So if we keep in mind that colors tell us about surface temperature, where blue is hotter and red is cooler, we can see that these patterns must be telling us something about the relationship between surface temperature and luminosity. So a Danish astronomer named Hertzsprung and an American astronomer named Russell recognized the relationships between surface temperatures and luminosities of stars. They built on the work of other scientists, but they independently decided to make these graphs of stellar properties by plotting stellar luminosities on the vertical axis and surface temperature on the other. These graphs reveal previously unsuspected patterns among the properties of stars and ultimately unlock the secrets to stellar life cycles. So then what is a Hertzsprung-Russell, or HR diagram? These are graphs made by Hertzsprung and Russell that we now call HR diagrams. And they are now a really important tool in astronomical research, and they're central to the study of stars. These graphs plot individual stars as points with their stellar luminosities on the vertical axis and their surface temperature on the horizontal axis. So it plots luminosity and temperature of stars. There's a couple of things we need to notice about an HR diagram. The horizontal axis here tells us about the surface temperature, which we discussed before corresponds to spectral type. So we see these spectral types O, B, A, F, G, K, and M listed on the bottom here. Temperature decreases from left to right because Hertzsprung and Russell based their diagrams on the spectral sequence. So on the right are cooler red stars. On the left are the bluer, hotter stars. So temperature goes kind of backwards of what we would think, from cool to hot. The vertical axis represents stellar luminosity in the units of the sun's luminosity, L sun. Stellar luminosities span a wide range, so to keep the graph compact, each tick mark represents a luminosity 10 times as large as the tick mark before it. So you see 1 is the actual luminosity of the sun. As we go up, these are ones that are greater than the sun. As you go down from there, these are luminosities less than that of the sun. So that's kind of how we would read these HR diagrams. So because luminosity increases upward and temperature increases towards the left, stars near the upper left are both hot and luminous. Similarly, stars near the upper right are going to be cooler, but still luminous. Stars near the lower right will be cooler but dim, and stars near the lower left would be hot and dim. So that's just one of the things that we could learn from this diagram. The HR diagram also provides information about stellar radii, because a star's luminosity depends on the surface temperature and its surface area or radius. If 2 stars have the same surface temperature, one can be more luminous than the other, only if its size is larger. So stellar radii must increase as we go from high temperature, low luminosity corners on the lower left to low temperature, high luminosity on the upper right. So these diagonal lines here represent different stellar radii, telling us the different sizes. So you see, for example, down here, these are very small stars, whereas you increase in the stellar radii, these stars are getting larger. So diagonally, the stars go from smaller to larger. So what we see with all this diagram is that most of the stars fall somewhere along what we call the main sequence, which is this prominent streak that runs from the upper left to the lower right on the HR diagram. Notice that our sun is one of these main sequence stars. The main sequence are these prominent line points that represent our main sequence stars from the upper left to the lower right on the HR diagram. So we can see this on all of them. If we go back to kind of a more empty one, this band here is our main sequence. So in the image on this slide, we just took out all of the other stars so you could clearly see that main sequence band. Then we see the stars in the upper right here are called supergiants. They're called that because they are very large in addition to being very bright. So these are the very large, very bright stars that appear at the top of an HR diagram. So supergiants are large and bright. Just below the supergiants are the giants, which are somewhat smaller in radius and lower in luminosity, but they're still larger and brighter than the main sequence stars. So giants appear just below supergiants because they're a little bit smaller in radius and a little bit lower in luminosity than the supergiants are. The stars near the lower left are small in radius and appear white in color because of their high temperatures. These stars we call white dwarfs. So they have a high temperature, but a low radius. White dwarfs are the hot, compact corpses of our low mass stars. They typically have a mass similar to that of the sun, but compressed to a volume about the size of the Earth. In addition to the four main groups that we just talked about, some stars fall in between categories. So for more precise work, astronomers assign each star to a luminosity class designated with a Roman numeral from 1 to 5. The luminosity class describes the region of the HR diagram that the star falls in. So despite the name, a star's luminosity class is more closely related to its size than it is to luminosity. The basic luminosity classes are 1 for supergiants, 2 for a bright giant, 3 for a regular giant, 4 for a subgiant, and 5 for a main sequence. So luminosity classes 2 and 4 are pretty intermediate to the other ones. We use both spectral type and luminosity classes to fully classify a star. For example, the complete classification of our sun is G2V. The G2 spectral type means that it's yellow, white in color. And the luminosity class V means that it is a main sequence star. Another example, Betelgeuse's M21. M2 makes it red. The 1 makes it a supergiant. So this kind of gives us an idea of its spectral type and its luminosity. So we can look at kind of its color and surface temperature and how bright it is and where it falls on the HR diagram by using both of these classes to define it. So the Hertzsprung-Russell diagram really gives us a lot of information. It gives us the temperature, the color, the spectral type, the radius, and luminosity. So it really has a lot of information about our stars for us. And one of the important things that it points out is this band of main sequence stars. Now we're going to start to answer the question, what is the significance of the main sequence? Most stars, including our sun, have properties that place them on this main sequence portion of the HR diagram. High luminosity main sequence stars have hot surfaces, and low luminosity main sequence stars have cooler surfaces. The relationship between luminosity and surface temperature comes about because a star's position along the main sequence is closely related to its mass. All stars along the main sequence are fusing hydrogen into helium in their cores, just like the sun is, and the mass determines both the surface temperature and luminosity, because these are the key factors in the star's rate of hydrogen fusion into helium. So what about the lifetimes along the main sequence? A star is born with a limited supply of hydrogen in its core, so it can only remain as a hydrogen fusing main sequence star for a limited time. That we call the star's main sequence lifetime. Because stars spend the vast majority of their lives as main sequence stars, we sometimes refer to the main sequence lifetime as simply the lifetime. So main sequence stars are the ones that fuse hydrogen into helium in their cores like the sun. The luminous main sequence ones are hot and blue. The less luminous ones are cooler and have yellow or red colors to them. Mass measurements of the main sequence stars show that the hot blue stars are more massive than the cool red ones. So towards the top of the main sequence, they're going to be larger. Towards the red, cooler portion, they're going to be typically smaller. The mass of a normal hydrogen-fusing star determines its luminosity and spectral type. So mass is what we call a star's most fundamental property, and that's important for you guys to remember. Astronomers began classifying stars by spectral type and luminosity class before they understood why stars vary in these properties. Today, we know that the most fundamental property of any star is its mass. And that's because a star's mass determines both its surface temperature and its luminosity throughout the main sequence portion of its life. And these properties then explain why higher mass stars have shorter lifetimes. So its mass determines how much hydrogen fuel the star initially has in its core, and its luminosity determines how rapidly the star uses that fuel. So the core pressure and temperature of a higher mass star need to be larger to balance gravity, and a higher core temperature leads to a higher fusion rate, leading to a larger luminosity. So the mass tells us how much hydrogen it has initially, while its luminosity tells us how fast a star uses that hydrogen fuel. So some stellar properties that we could review. Luminosity we get from brightness and distance, ranging from 10 to the negative 4th L-sun to 10 to the 6th L-sun. Temperatures we get from color and spectral type, ranging from cooler stars that are about 3,000 Kelvin to hotter stars that are about 50,000 Kelvin. And we get the mass from the period and average separation of a binary star orbit, leading from 0.08, the mass of the sun, to about 100 times that, the mass of the sun. So this is just kind of comparing them all so you can see that all kind of in one spot, but this is the same thing that we saw on the previous slide. So what about the mass and lifetime of a star? Massive stars start their lives with a larger supply of hydrogen, but they fuse that hydrogen into helium so rapidly that larger stars have shorter lifetimes. And that's because they use their hydrogen fuel quickly. For example, a star with a mass of 10 times that of the sun is born with 10 times as much hydrogen as the sun. However, its luminosity is 10,000 times that of the sun, which means that it uses that hydrogen at a rate 10 times as fast as the rate in the sun. With 10 times as much hydrogen being consumed at 10,000 times the rate, the lifetime of a 10 solar mass star would only be about 1/1000th as long as the sun's lifetime, which is about 10 million years only. Its actual lifetime may be a little longer than this because it can use more of its core hydrogen for fusion than the sun can. But the general pattern is the more massive stars live shorter times, sometimes even just a few million years. So here is a summary of everything we learned about the main sequence stars. High mass stars have a high luminosity, but they're short-lived. They typically have a larger radius and they're blue in color, while our low mass stars have a lower luminosity, but they live longer. They have a smaller radius and they tend to be red in color. Now that we've finished talking about those main sequence stars, we're going to get into what are giants, supergiants, and white dwarfs. So we said main sequence stars are the ones that fuse hydrogen into helium in their cores. What about the other classes of stars on an HR diagram? These other classes all represent stars that have exhausted the supply of hydrogen in their central cores, so they can no longer generate energy in the same way that our sun does. We're going to start by looking at the sizes of giants and supergiants. The bright red stars are giants and supergiants whose properties place them to the upper right of the main sequence in an HR diagram. So we know that giants and supergiants are stars that are actually near the end of their lives. And that's because they've already exhausted the supply of hydrogen fuel in their central cores. So they're kind of facing this energy crisis. Because without that energy coming out, they're trying to stave off the inevitable crushing force of gravity. So this crisis causes these stars to release fusion energy at a furious rate, which accounts for why they're so bright and have these high luminosities. And having this fusion energy at a fast rate causes their surfaces to expand to enormous sizes. Overall, though, giants and supergiants are rarer than our main sequence stars are. So we see that our stellar properties depend on mass and age. Those that have finished fusing hydrogen to helium are no longer on the main sequence. All stars become larger and redder after they use all their core hydrogen. They become giants and supergiants. But what we're going to see is most stars end up small and white after fusion has ceased and become white dwarfs. What happens is giants and supergiants eventually run out of fuel completely. A giant with a mass similar to that of our sun ultimately ejects its outer layers, leaving behind a dead core where all nuclear fusion has ceased. White dwarfs are these remaining embers from former giants. They're hot because they are essentially exposed cores of stars, but they become dim over time because they lack an energy source. A typical white dwarf is no larger in size than the Earth, but has a mass similar to that of our sun. So clearly white dwarfs need to be made of matter that's compressed to a high density, and this is unlike anything that we find here on Earth. So then this raises the question, why do properties of some stars vary? Not all stars shine steadily like our sun does. Any star that varies significantly in brightness with time is what we call a variable star. Certain types of variable stars cannot achieve the balance between the power coming up from their core and the power being radiated from the surface. Sometimes that causes the upper layers of a star to be too opaque to let a lot of energy escape. So what happens is the pressure builds up beneath the photosphere of these stars and the star expands in size. This expansion puffs up the outer layers until they become more transparent, and they're transparent enough for the trapped energy to escape. The underlying pressure then drops, which allows the contraction to happen until the trapping of energy resumes. So the stars are basically in this quest for a steady equilibrium. So the atmosphere of such a pulsating variable star alternately expands and contracts, causing the star to rise and fall in its luminosity. And that happens as it's trying to find a balance. So this shows us a typical light curve for a pulsating variable star with the star's brightness graphed against time. Any pulsating variable star has its own particular period between peaks and valleys in its luminosity, which we can easily see from its light curve. So for example, its period is from peak to peak, or we could also say the period goes from valley to valley. These periods can range from as short as several hours to as long as several years. So for example, the light curve of this pulsating variable star shows us that its brightness alternately rises and falls over a period of 50 days. Most pulsating variable stars inhabit a strip called the instability strip on the HR diagram, and this lies between the main sequence and the red giants. So that's what we're looking at here, and the red giants would be kind of in this upper right area. So a special category of very luminous pulsating variable stars lies in the upper portion of the strip, and they are known as Cepheid variable stars. They are significant both because they're so bright and because their pulsation periods turn out to be closely related to their luminosities. As a result, Cepheids played a key role in helping us establish the distances to many galaxies that are beyond the Milky Way. So they helped reveal kind of our overall scale of our universe. So in this section, we learned about Hertzsprung-Russell or HR diagrams and how they plot luminosity versus surface temperature. On the diagram, they show us that most of the stars fall into what we call main sequence stars, and these are stars that fuse their hydrogen into helium in their core. We also learned that a star's mass determines its position along the main sequence, with the high mass stars being luminous and blue, while the low mass stars are more dim and red. Then we learned about the giants, supergiants, and white dwarfs. We learned how the giants and supergiants are the stars that become larger and redder after all of their hydrogen is used in their core, whereas most stars kind of end their lives as tiny white dwarfs after fusion has ceased and all of the outer layers of the star has left. We've wrapped up that section by learning that some stars vary because they fail to achieve the balance between their power and energy in their core and the power that's radiated out from the surface. Now we're going to talk in this last section about stellar clusters. All stars are born from giant clouds of gas. Because a single interstellar cloud can contain enough material to form many stars, stars usually form in groups. In our snapshot of the heavens, many stars still congregate in the groups that they formed in. And these groups are known as star clusters, and they're really useful to astronomers for two main reasons. One, all the stars in a cluster lie at about the same distance from Earth. Two, all of the stars in a cluster formed at about the same time. So astronomers can use star clusters to compare the properties of stars that have similar ages. So in this section, we're going to learn what the two types of star clusters are and how we can measure the age of a star cluster. So our two types of star clusters are open clusters, which we see on the left here, and globular clusters, which we see here on the image on the right. And then the next two slides, we're going to go over the difference between these two types of clusters. So they come in two types. First, we're going to talk about open clusters. Open clusters are a cluster of up to several thousand stars. They're usually loosely packed, and they're found only in the disks of galaxies, and they generally are made up of young stars. And we see kind of the opposite when we look at globular clusters. These are densely packed. They have up to 1 million or more stars. We find these mainly in the halos of galaxies, and they contain only old stars. So we see kind of a big difference. The open cluster stars are young. There's a few thousand of them loosely packed in the disks of galaxies, where the globular clusters, there's 1 million or more stars in a dense ball in the halos of galaxies, and they're typically older stars. These two types of star clusters differ not only in how densely they're packed, but also in their ages, which we saw, and their locations. Our massive blue stars tend to die first, followed by our white, yellow, orange, and then red stars. We can look at the ages of star clusters. We can determine the age of a star cluster by plotting its stars on an HR diagram. This is an example for Pleiades. Note that most of the stars in this cluster lie along the main sequence with one important exception. At the upper end of the main sequence, stars start to trail away to the right of the main sequence here. That is, the hot, short-lived stars of spectral type O are missing from the main sequence. You see how we have no stars in this region. Apparently, the Pleiades cluster is old enough for hydrogen fusion to have ended in the cores of its main sequence O stars, but young enough that hydrogen fusion is still happening in the cores of some stars of spectral type B that remain on the same sequence. So what we see from this is that the Pleiades cluster now has no stars with a life expectancy less than around 100 million years. The precise point on the HR diagram where a cluster's stars diverge from the main sequence is what we call the turnoff point. The age of the cluster is equal to the lifetimes of the stars at its main sequence turnoff point. The technique of identifying main sequence turnoff points is our most powerful tool for evaluating the ages of star clusters. So that main sequence turnoff point of a cluster actually can tell us its age. And that turnoff point is where the cluster stars diverge away from this main sequence strip. To determine accurate ages, we need to compare models of stellar evolution to the cluster data. So what we've learned from detailed modeling is that most open clusters are relatively young, with a few older than about 5 billion years. In contrast, the stars at the main sequence turnoff point in globular clusters are usually less massive than our sun. Because stars like our sun have a lifetime of about 10 billion years, and these stars have already died in globular clusters, we conclude that globular cluster stars are older than 10 billion years. More precise studies of the turnoff points in globular clusters, coupled with theoretical calculations of stellar lifetimes, place the ages of these clusters at about 13 billion years old, making them the oldest known objects in the galaxy, and that implies that they began to form within the first billion years of the universe's roughly 14 billion year history. So in this section, we learned about the two types of star clusters. We learned about open clusters and globular clusters. Open ones are the loosely packed. They have a few thousand stars, and they're typically young, while globular clusters are densely packed, hundreds of thousands and millions of stars, and they're typically older. These also happen in the halo region, while the open ones typically happen in the disk regions of galaxies. We can measure the age of a star cluster because it roughly equals the life expectancy of its most massive stars that are still on the main sequence stage. So this wraps up chapter 15, where we learned all about how we survey the stars. We have classified the diverse families of stars that are visible in the night sky. And a lot of what we know about the stars and galaxies and the universe itself is based on the fundamental properties of stars that we introduce in this chapter. So based on this chapter, we want to keep these fundamental big picture ideas in mind. All stars are made primarily of hydrogen and helium at the time they form. The differences between stars are primarily due to differences in mass and their stage of life. Stars spend most of their lives as main sequence stars that fuse hydrogen into helium in their cores. The most massive stars, which are also the hottest and most luminous, live for only a few million years. The least massive stars are coolest and dimmest, and they'll survive until the universe is many times its present age. The key to recognizing the patterns among stars was the HR diagram, which shows us surface temperatures on the horizontal axis versus luminosities on the vertical axis. The HR diagram is one of the most important tools of modern astronomy. And finally, a lot of what we learned about the universe comes from studying star clusters. We can measure a star's cluster age by plotting its stars on an HR diagram and determining the hydrogen fusion lifetime of the brightest and most massive stars that still exist in the main sequence stage. So this wraps up chapter 15, where we surveyed the stars and learned about the properties of stars. And we also learned about patterns among our stars. And finally, we learned about star clusters. Make sure you check the online site for all of the course content and assignments associated with this chapter.